A quarterback can pass, run, fumble, or throw an interception, denoted P, R, F, or I. Let Xn be the sequence of those possibilities with the transition matrix given to the right. If the first play is a pass, what is the expected number of plays until the QB throws an interception or a fumble? What is the probability the sequence ends in an interception? Now, what we're talking about here is exit distributions and exit times. So we're going to use a formula for exit time, g of x, for this first problem. What is the expected number of plays until the QB throws an interception or fumble? So just note, looking at our matrix here to the right, F and I are definitely absorbing states, right? So this is going to end this sequence without question. Once we're in F, we're not leaving F. There's a probability of 1 of staying in F. And same for the interception, right? We can see that from our matrix. So what we're going to do here is we're going to set g of F equal to g of I equal to 0. And what we want is g of P, right? They say the first pass is a play. So we're going to do is use our function here to set up a system of linear equations and then solve that system of linear equations. So g of P equals 0.7 g of P plus 0.2 g of R. Now, since g of F and g of I are 0, I'm going to leave those as 0 and then add that 1. Now, the reason we add that 1 is because we have to account for a first play elapsing, right? So if we want the expected numbers of plays starting with the pass, we have to account for the pass. So that's why we add that plus 1. Now, g of R equals 0.35 g of P plus 0.6 g of R. And again, g of F and g of I equals 0, so I'm going to leave those out, and plus 1. And now what we have is a system of linear equations with two equations, two unknowns, so it's pretty simple. I will post a video to attach. It's a little bit tedious, not too bad with two unknowns, but I'm not going to do it now. But there's a lot of good videos on YouTube. Later on I will attach one. But just note, you can check this at home. G of P is going to equal 12. So the expected number of plays starting with a pass to end the sequence, i.e. getting to a fumble or an interception, is going to be 12. Now moving on, what is the probability the sequence ends in an interception? This is an exit distribution. And with an exit distribution, we're going to use a similar formula, but we don't have to account for the first event happening like we had to account for the pass happening for the exit time. So our formula is almost exactly the same, except we leave out that plus 1. And now we're not going to get an expected number of things, right? We're going to get a distribution. So just note that the question asks, what is the probability the sequence ends in an interception? So what we want to do here is disregard the sequence ending in a fumble and take into consideration, right, the fact that it's going to, the likelihood that it's going to end in an interception. So we're going to set h of f equal to 0 and h of I equal to 1. And then again, we're going to go along that top row using h of p. I'll just scroll up here and show you guys. I'm just going across that top row. Equals 0.7 h of p plus 0.2 h of r. Now, plus 0.1 h of I, and then since h of f equals 0, I'm going to leave this out. Now, h of r equals 0.35 h of p plus 0.6 h of r plus 0 h of I. And again, I'm going to leave out h of f because it equals 0. Now, note that this guy goes away and that this guy just equals 0.1. Now again, we're solving a system with two equations, two unknowns. It's pretty straightforward. I will post a video. Maybe I'll do these simultaneously for those of you that aren't that familiar with linear algebra. But being in this course, hopefully you are familiar with it, so I'm not going to do it up here, but just note that you can solve the system of linear equations pretty easily. There's calculators that'll solve it, or there's websites that'll solve it, or you can program it on your computer. However you want to do that, but just note that what we want is h of p because we started with the pass, and h of p ends up equaling 0.8, which equals 80%. So to answer the question, what is the probability the sequence ends in an interception? It's pretty high here. Starting with a pass, it's going to be 80% of the time.